In this video, we are looking at a particular type of work problem. They are the problems involving ropes, chains, and cables. Here's the idea. Often in these problems, we've got some rope or chain or cable, and it's sitting here, and maybe it's heavy, maybe it weighs 20 pounds. And we're moving it through some distance. So maybe we're just moving it 4 feet to some table height. If I want the work done and taking that whole thing and then moving it through 4 feet, work is very easy. It's just force times displacement. The force is going to be the weight of that chain or cable. So in this case, it would just be 20 pounds multiplied by 4 feet. So that's 80 foot-pounds of work. Now, most of the problems in this section are not like that. Instead of taking that whole cable and pulling it up through 4 feet all at the same time, so you've got it as one unit, like it's in your hand, and you're moving that whole unit up at once through 4 feet, or that you're moving that whole thing up as one unit through 4 feet. Instead of doing that, in these problems, we often have a cable or rope or chain like hanging off the side of a building, and we're pulling up a little bit of the rope at a time. And because of that, we're going to need calculus. So let me show you an example. So let's say you have a rope, and that rope weighs 0.75 pounds per foot, and it's 40 feet long. The rope weighs this many pounds per foot, and it's 40 feet long, and it hangs off of the side of a building. Okay. Here are 2 questions. How much work is done in pulling the entire rope to the top of the building? And then also, how much work is done in pulling half of the rope to the top of the building? Okay. So to set this up, the first thing I would do is draw a picture. It's always a good idea to start by drawing a picture. So this building is 100 feet tall, and I've got a rope hanging off the top of it, or hanging off the side of it, like this. Now, we are told that this rope is 40 feet long. So this distance from here to here is 40 feet. At this point, you can choose where you want to place your y equals 0 line. All distances are going to be relative to that choice. So if I choose y equals 0 to be at the top, and I choose this to be the positive y direction, then this is going to be y equals 40 down here. And that is totally fine that we've got y equals 0 here, and this is the positive y direction. Everything is good that way. You just have to stay consistent with your choice as you work through the rest of this problem. Okay, so I drew my picture. That's the first thing we do. And now we want to decide if calculus is required. So the question is, does the force vary? or does the distance vary for certain parts of this rope? Well, I think you guys can see if you're standing here at the top and you start pulling the rope to the top, the force that's pulling down off the side of the building, that's going to become less and less as you pull more of this rope to the top. It's going to be a lot lighter and easier for you when there's only a foot hanging off the side of the building than it is at the beginning when you've got 40 feet of rope that weighs 0.75 pounds per foot hanging off the side of the building. I'm still not sure that says the force acting on each piece varies, but it does tell us that that force is not the same the whole time, not for the guy at the top. So I'm thinking because of that, calculus is required. Another question you might ask yourself is, does the distance vary? Does the entire rope move through exactly the same distance? Here, when I took my rope as one unit and I moved the whole thing up 4 feet, the whole rope moved 4 feet. So yeah, calculus wasn't required there. I had the same amount of force acting the whole time, 20 pounds, and it's moving through. I'm moving through 4 feet the whole time. So we're good there. But does the distance vary for the pieces of this rope? I think the answer to that one is yes, definitely yes. This piece of rope at the bottom, at y equals 40 feet, has to move through 40 feet. But what about this one at 30 feet? It only moves through 30 feet. And the one at 20 feet moves through 20 feet. And the one at 1 foot only moves through 1 foot. And there's part of it that barely moves through any feet at all at the very, very top. So each piece of this moves through a different distance. And if you say yes to either one of those questions, that means calculus is required. And if calculus is required, we're going to do what we always do. We're going to break this up into n pieces and look at the work on one piece. So let's say this is my piece. It has a length of delta y. These are measurements in feet, so that's delta y feet. And the distance that piece moves through is this distance right here. So I've marked up my picture, and now I want to find the work on the ith piece. Now work is force times distance. The force acting on that piece times the distance that piece moves through. Now for these rope, chain, and cable problems, we're going to assume a constant force per unit length ratio. There's not going to be some part of the rope that has knots in it, which makes part of the rope heavier than other parts of the rope. That 75 pounds per foot is going to be consistent the whole time. This rope has the same force per unit length density, if you will. So this force can be split up into force per unit length, which happened to be given to us this time. But I have to multiply by the length of that piece to get the force acting on that one little piece. And then I want to think about the distance that piece travels through. These little eyes say I'm talking about a piece. I'm not talking about the whole thing, but a piece of it. Don't put 40 feet here for the length. We just want the length of the piece. Well, the force per unit length was given to us at 0.75 pounds per foot. And the length of that piece is delta y feet. So when we multiply those two together, the feet reduce, and you end up with 0.75 times delta y pounds. And that's good. Pounds are units of force, so we're good there. Now I have to think about the distance that piece moves through. Now, if I choose this to be the positive y direction, I know we're used to doing y top minus y bottoms. This change of orientation might make things a little weird. Now we're doing this y value minus this y value. It's the one that's associated with larger y values, which is farther toward the bottom, minus the one associated with smaller y values. So y top times y bottom this time gets flipped. It's sort of y bottom minus y top. But it's all because of this orientation choice. With that in mind, if this is y equals 0 and this is my distance, the distance is just going to be y sub I, because I decided this is the positive y direction. And if you don't believe me, think about what the distance is for that piece at y equals 40. Well, it's just 40. At y equals 20, the distance is going to be 20. At y, the distance is just going to be y. So this is y sub I feet. We multiply all those together, and we get 0.75 times y sub I times delta y. Feet times pounds is foot-pounds. Those are units of work. That's a good thing. And then if you want the total work, you want the exact work acting on the whole thing, you take the limit as the number of pieces goes to infinity, you add them up as I goes from 1 to n, and that's going to represent an integral. So total work is the limit as n goes to infinity of the sum of the work on each of those individual pieces, which is 0.75 times y sub I times delta y. That's foot-pounds. And that's the integral of 0.75 times y dy. And we're integrating wherever we're lifting that rope. So we're integrating from y equals 0 to y equals 40. All right, so just anti-differentiate. Substitute in 0 and 40 and subtract. So that's 3 over 4 divided by 1/2, that's 3/8 times 40 squared minus 0 at 0. And that ends up being 600 foot-pounds of work. We're required to move this whole thing to the top. Now, careful with the second piece. With the second piece, it says how much work is done in pulling half of the rope to the top. Well, I think we can just modify this integral that we just did. When I'm talking about the top half, well, I split the top half into little pieces. I find the work on the ith piece. The force per unit length stays the same. The piece is still delta y feet. The distance the piece moves is still y sub I. And all of this is going to be true for the top part of the rope. So for part B, the work to move the top 25 feet of that rope is going to be the integral, I said the top 25, the top half of these, the top half of the rope, and that's from y equals 0 to y equals 20. And then we've got this. That's what we're eventually going to integrate. So we have 0.75 y dy for the top. So we use our rules. Nothing has changed here. The only thing that's changed is my limits of integration. I'm integrating from 0 to 20. So I've got 3 over 8 times 20 squared. So that's 150 foot-pounds. Now, the bottom half of the rope, though, that has changed a little bit. So that first 20 feet, this is y equals 0 to y equals 20, we're handling that in exactly the same way as before. Each little piece only moves a distance y. But from y equals 20 to y equals 40, this bottom piece, well, that whole bottom piece has been moved up 20 feet. That's what happens if we're moving that top 20 feet off. This just moves up 20. So I don't think calculus is required here. I think work for the bottom piece is just the force acting on that bottom piece times the distance that that bottom piece moves through. And the force acting on the bottom piece is still that 0.75 pounds per foot times the number of feet on that bottom piece. Well, for half of it, that's 20 feet. So we have this many pounds of force acting on it, and it moves through a distance of 20 feet. So now we've got 0.75 times 20 times 20, and that is 300 foot-pounds of work to move just the bottom. So for part B, when it says how much work is done in pulling the half of the rope to the top, you have to be careful. This is the work in moving the top half of the rope. But the bottom half of the rope, it's like dead weight. So I'm just going to take this top half and add it to this bottom half. The bottom half does not require calculus, the top half does. And the total work, of course, is the sum of those. And so we end up with 450 foot-pounds of work. Any questions about that? All right. So that's our first example. Now for our second example, let's say you have a chain. Say we have a 20-meter chain with a mass of, let's say, 4 kilograms, and it hangs from the ceiling. Question might say, what is the work done in lifting the lower end of the chain to the ceiling? Okay, so here's our ceiling. That's our chain, and it's 20 meters long. Now I'm going to choose y equals 0 to be at the ceiling again. So initially, this is at y equals 20 meters. This is what it looks like before we start. Then, so this, after we move this 20-meter piece all the way to the ceiling, it looks like this. Now I'm going to draw it with a little distance between it, but it's actually like laying on top of itself. And this is acting at y equals 10 meters. So I guess this is sort of a before picture. And this is the after picture. This is tricky. This is a little trickier. So the first thing we always want to do is draw a picture, and we did. And then we have to decide, is calculus required? Remember, work is force times distance, or force dotted with displacement. Are all of the pieces of this rope that move, do they all have the exact same amount of force acting on them, or this chain that move? And do all of the pieces of this chain move through the same distance? Does this one at y equals 20 move the same distance as one at y equals 15? What about the one at y equals 10? What about the one at y equals 5? Does that even move at all? I think we can safely say that calculus is required, because the distance changes from piece to piece. The piece at y equals 20 moves a different distance than the piece at y equals 15. Okay. So with that in mind, we know we need calculus. What we're going to do is we're going to split the part of this that moves into n pieces. And then once we've subdivided into n pieces, we want to find the work done on each piece. Now, notice that the top half does not move at all. It's staying there. But starting at y equals 10 meters, that part, well, that stays stationary, but y equals 10.5, that moves a little bit. It moves from here to here. Y equals 20 moves from all the way at 20 all the way to the top. But the one at y equals 15 meters moves from 15, well, that's going to be 5 units of distance, right? From 15 over to 5. Where the one at 12 is going to move from 12 to 8. It's symmetrical. This piece down here, whatever that distance is between y equals 10 and the piece itself, like that distance is going to be doubled because we're just going to move that distance up here, that distance up here, that for y equals 20 it's going to go all the way up there, and so on. So let's think about subdividing into n pieces. There's a representative piece. It has a length of delta y meters, and now we want the force acting on that piece and the distance that that piece moves through. Now we're told that the whole chain has a mass of 4 kilograms, and it's a 20-meter chain. Now, for this, whenever you have a chain, rope, cable problem, you always want to do force per unit length times the length of the piece. That has not changed. But notice that our system of units has changed. This time I don't see force anywhere in here. This is distance or length. This is mass. As soon as I see mass, as soon as I see meters and kilograms, I know I'm in SI units. I'm not in English units anymore. There are no pounds or feet anywhere in this problem. So when I am trying to get force, I'm going to have to use the fact that force is equal to mass times acceleration. So we've got force per unit length times distance. And force is mass times acceleration. It's acceleration due to gravity. And I'm going to write that as mass per unit length times acceleration. And if you don't believe me, write that as itself over 1. You see force, mass times acceleration is force, length times 1 equals length. And then we're multiplying by the length of the piece. And then I'm just going to use d sub I for distance because I'm running out of space over there. Okay, so I've got mass per unit length. So this particular chain weighs 4 kilograms, and it's a 20-meter chain. And acceleration due to gravity, that's what we always multiply by when we're finding the weight of something. In SI units, that's 9.81 meters per second squared. And then we're going to multiply by the length of that piece, and the length is delta y meters. And so notice these meters and these meters cancel, and I've got a kilogram meter per second squared. That's a Newton. And then the distance this piece travels through, that is the tricky part of this problem. We're going to figure out what that is. I'm just going to simplify this now. 4 goes into 20 5 times, so I've got 9.81 divided by 5 newtons, or times delta y. All of that gives me newtons. So that's my force, and now I'm trying to find the distance, that other piece. Well, we were just talking about it. The distance is going to be that distance right there, but doubled. Whatever that distance is, it's going to travel that same distance on the other side. Now be careful here. Everything is a little different than we're accustomed to because this is the positive y-axis. Y top minus y bottom doesn't quite work because of where I put y equals 0. If I put my y-axis in the same direction as usual, then we could do y top minus y bottom. But now when we take the larger y values and subtract the smaller ones, the larger y values are closer to the bottom, because y equals 20 is here, y equals 10 is there, y equals 0 is there. So we want to do larger y minus smaller y in order to get real distances. I don't want to do 10 minus 20 and get negative 20 meters. It doesn't make any sense. I would want to do 20 minus 10 and get 10 meters. So I want to do this one minus this one to get a positive distance, and then I want to double it to get the total distance. Well, in general, if this is the positive y-axis, this distance is just y sub I. And this distance, well, that's y equals 10. So this distance right here must be y minus 10. And then we're going to double it to get the total distance that piece traveled. I know it's a little tricky. It's the larger y minus the smaller y. So that's y minus 10. So if y is equal to 15, it's going to be 15 minus 10. It's going to give you 5. And the distance that piece travels through is twice that. So if this was at, let's say y was 18, I'd do 18 minus 10, I'd get 8. And the distance it would travel through is this 8 units plus the 8 units it goes up. So it'd be 16. So this is going to be y sub I minus 10, which is a positive number, times 2 for the distance that one piece travels through. And that is in meters. Notice that we had to multiply by 9.81 meters per second squared, and that was because we were given mass and distance, given mass in kilograms and distance in meters, rather than distance in feet and force in pounds. So as soon as I see pounds in feet, I know I don't need to multiply by acceleration due to gravity. As soon as I see kilograms in meters, anytime I need a force, I need to multiply by that acceleration due to gravity. Okay, so this is a work on one piece. Total work is the limit as the number of pieces goes to infinity of the sum as I goes from 1 to n of these guys. So I'm going to have 2 times 9.81 all divided by 5. Delta y I'm going to bring out to the side. That's taken care of, that's taken care of, that's taken care of, and now I need the y sub I minus 10 right here. And that is an integral. So I've got 2 over 5, you can call that 0.4 if you want to, times 9.81 times y minus 10 dy. And we're integrating for wherever we have pieces that are actually moving. Remember, we're only moving those pieces on the bottom. So those pieces over here get flipped so that they're moved up toward the top. So we're integrating from y equals 10 to y equals 20. All right, so let me bring my constants down. The antiderivative of y, that's a power rule. Add 1 to the exponent, divide by the new exponent. Antiderivative of a constant is a constant times my variable, which in this case is y, and we integrate from 10 to 20. So I'm going to have 0.4 times 9.81, which is 3.924. And then I've got 1/2 of 20 squared minus 10 times 20. All of that minus 1/2 times 10 squared minus 10 times 10. So that's 400. Half of 400 is 200. We've got 200 minus 200 there. So that's 0. And then over here I've got 100 times 1/2 is 50. And I'm subtracting 100 from that. So I have a negative 50 times a negative 1 is positive 50. And of course you could use your calculator for all of this arithmetic. This class is about calculus, not arithmetic, although arithmetic is important too if we want answers that make any sense. Actually, it's going to be exactly equal to 196.2 units of work. So what are our units? Well, these are newtons times meters, so it's a newton meter. And if you take physics class, you'll see that a Newton meter is the same as a joule. That's 196.2 joules. And so those are our rope, tank, chain problems. One thing to keep in mind is these are always handled almost always the same way. If calculus is required, so our force is varying or the distance that piece is moving through is varying. With these problems, we tend to write force per unit length times length times distance. And this is the length of a particular piece, and that's the distance a particular piece moves through. It's not the length of the whole chain, and it's not the distance that the whole chain moves through, or rope. And this force per unit length is going to be given to you in some way. Sometimes they tell you it's this many pounds per foot, and you can just fill that in. Sometimes they'll say it's 100 pounds, and it's 4 feet long, so you would say it's 25 pounds per foot. Wow, that's really heavy. So sometimes you've got to calculate this, and sometimes it's given to you. And remember, with SI units, mass is in kilograms, or tends to be given in kilograms. Force is in newtons, which is a kilogram times a meter per second squared. And we often have to multiply by acceleration due to gravity, which is 9.81 meters per second squared, because force is mass times acceleration. Oops, they're going to give you mass, and you might have to multiply by acceleration because that's how you get force. Now, in English units, force is typically given in pounds, and that is just straight given to you. You don't have to calculate the number of pounds. Mass is given in slugs, but I have never heard anybody tell me how many slugs something was. They just usually tell me its weight in pounds. So if you see pounds, you know you're in English units, and here distance tends to be measured in feet, and here distance tends to be measured in meters. And if I take a force of a Newton and I multiply it by a meter, the units for work are joules. And over here, if I'm taking pounds and I'm multiplying them by feet, force times distance, the units for work are foot-pounds. I know it seems strange, but that's exactly correct.